Hello, everybody. I'm the chair of the next session. My name is Svetlana Berdugin. I'm from Kiepenheuer Institute for Solar Physics in Freiburg. And I'm very happy to chair this last session. You're very welcome to this grand finale of Cool Stars 20. And we have one invited talk, two contributed talks, and two prize winner talks. So celebrity talks. Looking forward to that. So I'm very happy to invite Marley from NASA Ames. He's talking about the new set of atmosphere models, starting from about temperature in this room up to about temperature in the hottest exoplanets. So please talk about this.
Well, good morning. It's great to be here at Cool Stars and tell you a little bit about some of the progress we hope we're making in the theory of substellar atmospheres. And I want to also, the talk is really not so much about our own models, but about what's the best way to incorporate modern methods like retrievals with traditional methods like forward models and trying to understand the objects. I want to start, though, if you'll allow me, just one slide since we've been looking back. And it turns out that Cool Stars 15 in 2008 changed my life because I took my, well, this isn't not a good start. What? What do I? There it goes. Changed my life. I took my family, we stayed in the dorms. My daughter loves St. Andrews. She went there, she graduated last month, and my younger daughter's going next month. So Cool Stars changed my life. If anybody, I don't know if any of you brought your own families, but if so, you should, given my experience, you should start saving up for BU. Okay, thank you. So what do I want to talk about today? I want to talk about new forward models. What's the utility of forward models? Sometimes if you read our proposal reviews, you think we're proposing to use the harmony of the spheres to study brown dwarfs. But there's a really big value for understanding the atmospheres, and that's what I want to try to convey today. But yet we also need to use more modern techniques, retrieval techniques, sophisticated ways of comparing models to data, and figure out what's the best way to kind of triangulate on the properties of these objects. And so I'm going to be using this logo to try to tie together the different techniques and give examples of how we can use these different methods to try to better improve our understanding. So first of all, a little bit of it's not what the title says, but this is a little bit of what do I mean by the terminology? Forward models are using our best understanding of the atmosphere, radiative convective equilibrium, opacities, putting it all together, predicting what the temperature profile and the emergent flux looks like. Fitting methods can be as simple as chi-squared, which, as Mike Cushing showed over a decade ago, is very challenging for brown dwarfs, or using very new sophisticated techniques like machine learning or Starfish, which I'll talk about, to try to choose which is the best grid model that best describes an atmosphere. And finally, by retrievals, you mean the efforts to use tens of thousands, hundreds of thousands, millions of simplified, parameterized temperature profiles to predict spectra with various abundances, compare that to data, and then to try to extract empirical model parameters. So how do we use these things together? Well, first of all, why do we even need forward models at all? First of all, we need them as boundary conditions for the evolution. The atmosphere controls the rate at which the body loses energy to space. We have to have forward models to compute the trajectory through time of a brown dwarf. They give us grid models for characterization. They help us understand what's important. It gives us intuition into what matters, what doesn't matter. And it's a guide to where to search for new discoveries. Where should we go look for new molecules, for example? Retrievals alone can't do all this. We also need forward models to see if we consistently understand abundances, chemistry, gravity, all of these things together. Retrievals alone give us numerical values for these things, but they don't give us a perspective. But does it matter? What is this number telling us? Of course, I would like forward models. My first science paper I ever wrote was in 1986 with Bill Hubbard and Jonathan Lunine, where we presented grid models for brown dwarfs. If you look at historically, I grabbed 4 papers of grid models from our own group, Franz Allard with the Phoenix models. These papers alone have thousands of citations, so clearly it's important and it's useful for the community. There's a whole new generation of young people producing forward models. Pascal Triblin has very clever ideas about composition gradients, producing steps in the temperature profile. There's new models from Charnay et al. Who have looked at the new ideas about the LT transition. And at this poster, Mark Phillips has a poster about another new set of models. So there's a whole new generation coming online, and it's important that we compare the old generation, the new generation, and all these different ideas. So for that reason, we kind of need a new set of models now. This is Jackie Faraday's figure showing color magnitude diagram, and there's the sequence, the field sequence of brown dwarfs, but also this offset low gravity track for low gravity objects that also seems to be followed by young companion objects. So what's going on with that? Why are they offset? There's the discovery of the subdwarfs, and of course the directly imaged planets, lots of updates in the opacities from exomol. And so we need new models. Our group has been a little distracted by the exoplanets, and so it's nice to get back to where we all started. So this is some figures, a couple of figures from Mike Liu. Here's the normal, again, the normal field sequence. This is J versus J minus K, the young low gravity objects, and they're in a different track. For the rest, and so you can compare that to what's been done before. Here's our Simon and Marley 2008 models. Our tracks, first of all, don't fit even the field sequence that well, and we certainly can't fit these objects. Our hybrid models, cloudier, do vaguely better with the field, not really, and again, just we cannot fit the low gravity objects. And BT settle doesn't do it either, especially these very low, faint red objects. Interestingly, Will Best, who has a great poster here, has scrubbed the color magnet, the objects in the volume-limited 25 parsec sample with 150 new Euclid parallaxes and also the Gaia parallaxes, and has tossed out the binaries and spectral blends, and the color magnitude diagram goes from this to this, which is much cleaner, and with this intriguing gap right here at the boundary between the L's and the T's. So this is really the state of the art in what we're trying to compare to, at least for the field sequence. So we have a whole new model set. The basic physics is well established. I won't go into it. We have a review paper with Ty Robinson that talks about the modeling process I can refer you to. But what isn't clear cut, we have the physics, the basic physics, but of course the hard things are the chemistry in the clouds. That's not news. In particular, there's Rainout, which is how do you go about removing grains from the atmosphere, and the details of how you do that. We're using a technique, the approach of Shannon Vischer, who was previously, in our previous models, we used Katharina Lauders, and Shannon was Katharina's postdoc. And the big problem, of course, is what do you do about clouds? And we're continuing to use in our set the Ackerman and Marley clouds, but I'll talk about how we know that isn't the end state. There needs to be improvements. So here's more details in the models. In particular, we're looking at metallicities from -1 to +2 and a range of C to O values. Those are ratios to solar. So in this case, 1 means solar. It's a terrible nomenclature. But we already have online today cloudless models for solar, and we will soon have the red X's. And ultimately, the goal is to cover this whole parameter space and have that all online. We've always resisted naming our model set. It always struck us as a little bit presumptuous, but then we realized that everybody makes up model sets for model names for us, and then that's even more confusing. So many of us love Tucson, and so the Sonoran Desert, so we're calling them the Sonora models. We're posting not only the model spectra, but the underlying temperature and pressure profiles and the chemistry So you can compare, you can plot the models, look at the chemistry, and see how that compares to others. What we don't do is make the code open source, and we can argue about that in Q&A if you feel strongly. So here's what the models look like. This is a nice figure Caroline Morley made. Our 2012 models are in red, the new ones are in blue. You can see a fair bit of difference here in the red optical. Almost all of this is because we changed to Nicole Allard's new alkali opacities. The source of the optical opacity was a mystery. In the first generation of brown dwarf models comparing to Gliese 229b, all the models were way too bright in the optical. And there was some time before it was determined the mystery absorber was the alkalis. The new the new Nicole Allard opacities are stronger on the wings, and so the new models are darker. There's also differences in detail because of methane and new water opacities in particular. So the first result, now kind of using models to study brown dwarfs, is we have a new value for the hydrogen burning minimum mass. This is Didier Simon's work. The minimum mass has gone from 0.075 to about 0.073 because there's a little bit more opacity, around 1800 Kelvin, which allows it to burn hydrogen to lower temperatures. You've seen this plot already several times today. I just put 3 transiting brown dwarfs with known radii for 3 different years in green, 700 million to 1 billion to 10 gigayears. And that little movement is the difference in the hydrogen burning minimum mass. I think this is going to continue to jitter around as people make other improvements to the opacities. So how do they do in color magnitude space? Each dot is one of our models. Like I said, these are already online. We do in J versus J minus K in the L dwarfs, starting at 2400 Kelvin. Does really good job. This is the best we've personally ever done in the early L dwarfs. There's no clouds, and the models seem to span the range pretty well, and into the mid-Ts where again, there's no clouds. But of course, the cloudless models don't fit very well at all where cloud opacity is important. Here's a low metallicity track, M over H of -0.5, and so these look promising for the subdwarfs. So what do we do with this? Now we have thousands and thousands of models. What's the best way to fit the models to the data? And this is something that I think the community is working on. I know there's approaches to use machine learning. We've been experimenting with Starfish from in Cheskala 2015, and Michael Gully Santiago, who is here, has been modifying Starfish to do brown dwarfs. In a word, Starfish is a method to use grid models on a specified set of parameters and then be able to smoothly interpolate within them and give nice posteriors to really nail down what the range of parameters are that fit any given spectra. We've been doing it both on IGRIN spectra, which is shown here. These are effective temperature and gravity measurements as a function of spectral order, which isn't physical, but just shows you we're not getting a consistent answer with wavelength. Zijie Zhang from the University of Hawaii has been also using Starfish with low spectral resolution data, and I'll show you a little bit about how that's going. Here's a model spectrum, a real spectrum in black from Specs. The chi-squared fit in this case is the blue, Starfish is in red. In this case, they agree almost perfectly. Effective temperature about 950, log G about 4.2. Nice thing about the chi-squared value, the chi-squared value just gives you one number. Starfish, we can see the posteriors and understand where the best fit is in log G and effective temperature space. But what we really want to do is compare this now to the retrievals. So Mike Line at Last Cool Stars presented results on retrievals of about a dozen mid-T dwarfs. We've used exactly the same objects and run our new models on them. And what we find is we can run Starfish. Here's the best fitting temperature pressure profile. We can see where the models are for this object. It's a peculiar T8. Here's what the retrievals look like from Mike Line. Here's what the atmosphere model for the best fitting effective temperature and gravity from the retrievals. And we put all 3 of them together, there's really good agreement. wow, we understand this object, we think. It's really on an adiabat. There's not any sign of a temperature jump. A little bit of variation higher in the atmosphere where the retrievals don't do as well. We can look at the posteriors. The Starfish retrievals, I really agree. It's high gravity, temperature around 780. It's like, wow, we seem to understand the physics of these T-dwarfs. But we go to another object. This is a T7.5, and things are completely discrepant. The Starfish wants to have there's two solutions. The retrievals have a different solution. Another calculation gives yet a third one. The temperature profiles are very discrepant. So what's going on? This is the value of doing retrievals and forward models at the same time. It's telling us we're missing something, and we need to study these objects in detail to understand why the models are failing. If we just had the retrievals or we just had the forward models, we wouldn't recognize this problem. Here's a comparison of effective temperature from the retrievals versus our grids, and there seems to be a systematic 50 or 80 Kelvin offset. Why is that? We have to figure that out. So again, an example of all three things coming together to give insight. What about a case where the retrievals have validated the ideas from the forward models? In the forward modeling, you have to make a decision of how do you treat the rainout of grains? Do you leave grains in chemical equilibrium with the gas, or once you form a grain, do you settle it out of the atmosphere and remove it from the chemistry? The sodium and potassium are great for that. If you leave them in equilibrium, they react with grains and come out of the atmosphere around 1100, 1200 Kelvin, like the dashed line. If you remove the grains, the more refractory grains, the alkalis stick around to about 600 Kelvin. The retrievals in blue are from Mike Line's work before. Joseph Zaleski has a great poster showing results now doing retrievals on Y dwarfs. And it's really clear. You can see the rainout of sodium and potassium. And so this really validates the rainout idea. It's clearly what's going on. People are still using the Cond chemistry from almost 20 years ago. Nothing wrong with it for its time, but it uses pure equilibrium. It's not what's actually happening. So going forward, we really have to do rainout. What about clouds, our favorite subject? Back to the color magnitude diagram. Here's one set of our cloud models for F set of 3, which is our cloud parameter. High gravity on the left, low gravity on the right. So the low gravity, it's good that it's on the right, but you can see with F set of 3, they turn too soon. It's interesting how the high gravity sticks around, but still comes across. So what are we doing wrong? What's wrong with these models? So this is a great example let's turn to retrievals to help us figure out what's wrong. And I'm going to be showing you an example of an object right in here, a very red L6. So Ben Birmingham, who was at NASA Ames a while ago, has developed his own retrieval code called Brewster, named after his dog. Ben is the one on the right. So he can have this is a great tool he has developed. He can have slab clouds, he can have deck clouds, he can have gray clouds, he can have clouds that follow the me properties of a given species. All kinds of great stuff. I don't have time to say how great it is. But here is TMAS 2224. The data is in black. If you just retrieve and just do fits to the specs data inside the dashed line, the models are nowhere near right. If you do a retrieval to specs data, you can fit the near infrared, but look how far off you are if you include IRS or the L-band spectra. And this is a contribution function plot that shows how high in the atmosphere on the right-hand scale you're looking. If you include those longer wavelengths data, you're sensitive to what's going on higher, and you can also see features like this little dip that we think is silicates. So Ben has run his framework on this, and the amazing thing is this confirms our overall understanding of how L-dwarf atmospheres work. He finds if you're into the Bayesian stuff, there's BICS on the right, but the very best model from retrieval is to have a high silicate cloud, optical depth of about 0.2, and a deep cloud decade of iron. The retrieved temperature profile is in here, and right where the profile crosses the condensation curves for iron and silicates is where the retrieval, which doesn't know anything about the chemistry, wants to put the clouds. our own forward models don't look like this. Unlike the case of the T-dwarfs, where at least where the shape is right, we get the right adiabats, it looks different. And we need to understand, this is a great example of why we need to do both to understand what's going on here. Is there some heat mechanism? Are we heating the upper atmosphere somehow? Is there wave breaking? What's going on? Here's the retrieval fit. You can't even see it, so I'll zoom in. Before I do that. Here's this 10 micron dip. This we suggested in Cushing et al. 2006. This was from silicates. Now let's zoom in. The retrieval is in the color. The data is in black. It looks good in the near infrared. And at longer wavelengths, look at that beautiful fit of the silicate feature from the silicate cloud that the retrieval wants to put in. Diana, how is it different? What are we learning from this? Our Ackerman and Marley, our forward model for the clouds, wants to make 5 micron silicate clouds. Brewster wants to make submicron clouds, put them up there. So it's much smaller clouds. Why is that? Diana Powell is going to tell you why in the next talk. But it's a great example, again, of the feedback between these different things. So what are some of the remaining issues? I've sped through this. Exactly how does the Rainout chemistry work? What do we have to do to get Rainout right? What's the recipe? And there's a lot of judgment right now that needs to be turned into a set of rules, which we don't know yet. How do we do the clouds in 3D? What's the right way to do retrievals on clouds? This is a big problem for exoplanet transits too. What's the right level of complexity? How do we model these clouds? The variability is going to tell us a lot about that, and we'll hear more later. The low gravity sequence, we still don't have that solved. L to T transition, all the other good stuff. So I want to insert an ad for LUVOIR. With my exoplanet hat, I've been participating on the SDDT for LUVOIR. It's an amazing concept, really considered by the 2020 decadal study. And our interim report just came out. Here's an idea of things it could do, UV spectra of M dwarfs to 25th magnitude. So yeah, LUVOIR, take a look at the interim report. So back to the brown dwarfs. In conclusion, brown dwarfs are hard. There's all this stuff going on, the chemistry, the clouds, all the details and how to model them. We've got to leverage all of the tools we have available. Forward modeling, retrievals, sophisticated ways of fitting models to data. And we're still working out how to do that. In addition, how do we use the high resolution data? The next generation of instruments is going to give it, like IGRINS is giving us very high spectral resolution data for brown dwarfs. How do we incorporate that with the low spectral resolution? What makes sense for that? And I think we're working that out in the next several years. We need more microphysical models. The models, I think, in what we have so far are definitely making progress, but we need to confront the data and learn more. So I'll leave it there. Our first set of models is already online. Use them, compare them to what other people are doing, and let's figure these objects out together. Thank you.
Thanks so much. Wonderful overview of the subject. Very exciting. So start from here. Questions. And then switch on the other side. Who was there? Okay.
Stan Mitch of University of Western Ontario. Thanks for another wonderful lesson in theory. Early on, you showed a comparison of the new alkali opacities to the previous ones, and the new ones seem to include some discontinuities. They're higher. Could you comment on what the physical motivation for that is?
It's the pressure broadening of the fundamental line, and these are all numerical results and at specific densities, and there are a lot of, it's a really hard calculation, and I think those discontinuities aren't real, but it's the best we can do to adapt the data that's available. Certainly we need better laboratory data on sodium potassium at these kind of conditions. So it's not real is the answer to your question.
Tzvi Maze from Tel Aviv University. Thank you for this very nice talk.
Thank you.
Just a comment about fitting models to data and using the chi-square. This is sometimes can be dangerous. First of all, because you have to assume a normal error. And the other thing is that chi-square is not sensitive to where you get the difference between the model and the data. So, for example, if the residuals concentrate in one part of the spectrum, or they are distributed all over, chi-squared.
Question, please.
Did you try?
Well,
Did you try other methods?
No, that's the point of like Starfish. These new methods are trying to be better than chi-squared. And Mike Line showed 15 years ago that for brown dwarfs, the chi-squared is terrible. But it's a point of departure. So, I agree with you. We have to do something more sophisticated.
Hi, Kelly Cruz, CUNY Hunter College. Thank you so much. This was great. I love seeing how all the different modeling techniques complement each other. On that note, so I'm super also excited about thinking about how small grains, how the theory is going to tell us how the small grains might be impacting the observed spectra of the L dwarfs. My question is that when are you going to do another model grid set that incorporates small grains? Or is Sonora going to be are we done with model grids and we're only going to do the forward modeling?
Well,
Never done.
we're going to have our standard FSET grid because there's a legacy value to that. Diana Powell is going to show you much more sophisticated models that have promise, but they're too slow to us to incorporate yet. So we're going to have to figure out how to do that, and we haven't done that yet.
All right, next question, yeah.
Baylor University of Edinburgh. Okay, so you showed some of the newer models, fluid models that don't have clouds in them. Or you mentioned them. The vast majority of forward modeling does incorporate clouds. So I have a specific and more general question, more philosophical question. So for retrievals, are there any attempts to use non-equilibrium chemistry or thermochemical instability in retrievals? And referring back to the models that don't have clouds and use thermochemical instabilities instead, in your opinion, can you model late L dwarfs into the T transition without clouds?
No. But the answer to that is probably longer than we can get into right here. But like Ben's temperature pressure profile, it could have a kink in it. There's no reason he couldn't have retrieved a thermochemical instability. And vastly, like in this BIC criteria, it did not want to do that. It wanted to put in clouds. I lost the thread of the rest of your questions, but yeah, it needs to be, and in fact, for all of our retrievals, we do it with chemical equilibrium and without. It likes the disequilibrium strongly too. So I think we know it's disequilibrium. We're still working on exactly what the clouds are, and we need to do retrievals for hundreds of objects, and ones that we have the masses for, and and ones we have the radii for, and the ones that have other independent constraints.
All right. Couple very short questions. Yes, this and then.
Serge Dietrich from Carnegie DTM. This is great. We've been talking about this all week, and I'm happy that it's finally here. Could you comment on the metallicity question, specifically how small offsets in metallicity might change the opacities, and how well do we know that?
You're thinking particularly the hydrogen burning minimum mass, or just in general? Yeah, no, the metallicities definitely matter, and we're almost done with our subsolar. I hope very soon we'll have them online, but it's very sensitive. You start dialing the metallicity back, and you start to see it pretty soon. The problem is, of course, as always, you're feeding back into these other effects, the disequilibrium chemistry, C to O ratio, the cloud physics, exactly what you're assuming. But I think it's a pretty clear distinction, especially going to lower metallicity.
All right, here.
Ian Crossfield, MIT. Mark, could you talk briefly about the plans you mentioned to make some of this code publicly available?
So the cloud model is openly available. Natasha Batala is working to bring many of our codes, like our albedo code that we use, to make it publicly available. This particular code has legacy back to the 1970s, and we're just not going to do that. So we're working on generating a new forward model that would be publicly available. It would make zero sense. I would die on this hill, and I may have to, but we're not going to make this code. It's just too hard to support.
All right, very short questions last. And then we switch to another talk.
Jürgen Schmidt, Hamburg Observatory. We know some of these late-type objects are very rapid rotators. So why is that not an important factor in your modeling?
Because they're so degenerate, if you actually calculate the oblateness, say, of these objects, they don't start, for a field mass object, they don't start to get really oblate until, down to an hour. So it's something to look at. Certainly we have looked and published on the effect of oblateness on the polarization, and there may be a signature there. It just doesn't, like now limb darkening and so on, because of the scale height compared to the radius, it's just not an important issue for us. Yeah.
Thank you a lot again. Wonderful talk, wonderful discussion. Thank you all. So.